What is light? It's a simple question with a mind-bending answer. Is it a gentle ripple like a wave spreading across a cosmic pond? Or is it a stream of tiny bullets, a barrage of particles zipping through space? For a long time, the greatest minds in science were certain they had the answer. They saw how light bent around corners, how it created interference patterns of bright bands, dark bands, just like waves of water do when they meet. It seemed obvious. Light was a wave. This elegant idea, championed by giants like James Clerk Maxwell, painted a beautiful picture of our universe, one filled with electromagnetic waves of all kinds, from radio to gamma rays. Then, along came a young patent clerk in Bern, Switzerland. His name was Albert Einstein. In 1905, a year he would later call his miracle year, he wasn't just thinking about clocks moving trains. He was wrestling with the very nature of light itself. The wave theory was nearly perfect. It explained so much about how light behaved. It was the bedrock of 19th century physics, a towering achievement of human intellect. But there was a crack in this beautiful foundation, a small, annoying experimental result that just wouldn't go away. A mystery that the glorious wave theory couldn't solve. This stubborn puzzle was called the photoelectric effect. Imagine you're a scientist in a lab around the year 1900. You have a piece of metal and a light source. Your goal is to use light to knock electrons free from the metal's surface. According to the trusted wave theory, a very dim light, if left shining long enough, should eventually build up enough energy to free an electron. It's like a gentle but persistent series of waves, slowly eroding a cliff face. You also believe that a very bright light, a truly powerful wave, should be able to blast electrons out with tremendous speed, regardless of the light's color. It just makes sense, right? More power in, more power out. But when you run the experiment, the metal is stubborn. It doesn't follow the rules. You can shine a very bright red light on it for hours, a light with immense intensity, and absolutely nothing happens. Not a single electron budges. It's as if the metal is completely ignoring your powerful beam of light. It's a baffling result. According to the wave theory, this should be impossible. Then, you try something different. You switch from the intense red light to a very, very dim violet light. Instantly, electrons start flying off the metal surface. It happens in a flash, with no time delay at all. Albert Einstein looked at this perplexing puzzle and proposed an idea so bold, so revolutionary it seemed almost absurd at the time. He said, "Let's forget the idea that light is only a continuous wave. What if light also travels in discrete, tiny packets of energy?" He called these packets quanta, we now call them photons. This wasn't just a minor tweak, it was a radical departure. Einstein imagined light not as a flowing river, but as a hailstorm of tiny, energetic bullets. Each photon carries a specific amount of energy. That energy is determined not by brightness, but by color. This one powerful idea explained everything perfectly. The reason the bright red light did nothing was because each individual red photon didn't have enough energy to knock an electron free. It didn't matter how many low-energy photons you threw at the metal. Like throwing a million ping-pong balls at a bowling pin, you can throw them all day and never knock it over. You need a single high-energy hit, like a baseball. Dim violet light was made of high-energy photons. Even if fewer in number, each violet photon could free an electron on impact. That's why the effect is instantaneous. A single violet photon strikes an electron. Boom, electron ejected. Think of a vending machine that only accepts $1 coins. You can feed it 100 pennies. Low-energy red photons, but it won't dispense. Insert one $1 coin, a high-energy violet photon, and it dispenses instantly. Einstein's explanation of the photoelectric effect did more than just solve one nagging problem. It blew the doors wide open on a whole new way of looking at the universe. It gave birth to quantum mechanics, the idea that energy could be quantized, that it comes in discrete little chunks, was the first step into a bizarre and wonderful new realm of physics. Light was not just a wave, and it was not just a particle. It was somehow mysteriously both at the same time. This concept, known as wave-particle duality, is a cornerstone of how we understand reality at its most fundamental level. The discovery wasn't just an abstract intellectual exercise. It has profoundly shaped the world we live in today. The principle that Einstein uncovered is at the heart of countless technologies that we often take for granted. Digital camera, solar panel, farm, night vision goggle. Every time you use a digital camera, you are using the photoelectric effect. The sensor in that camera is a grid of tiny electronic detectors that convert the light photons hitting them into an electrical signal, creating your picture. Solar panels, which power our homes and spacecraft, are essentially giant devices designed to harness the photoelectric effect, converting the energy of photons from the sun into usable electricity. This quantum leap in understanding has continued to ripple through science and technology for more than a century. It paved the way for lasers, for transistors, the building blocks of all modern electronics, and for medical imaging devices that can peer inside the human body. Even the automatic doors at the supermarket use a beam of light and a detector, operating on the same basic principle. The world of 1900, a world of steam and gears, was transformed into our modern electronic age, all because of a deep question about the nature of light and a stubborn piece of metal. So the next time you see the glint of sunlight off a window or snap a photo with your phone, take a moment to think about what's really happening. You are witnessing a storm of individual photons, tiny packets of energy, traveling across space to complete their journey by interacting with matter. The universe, at its smallest scale, is a frenetic dance of quantum particles. Einstein's work on the photoelectric effect didn't just earn him the Nobel Prize, it gave us a new set of eyes to see the cosmos. And it leaves us with a lingering question. If something as familiar as light can be so strange, what other secrets is the universe waiting to tell us?